All right, AP Chem, here are your most missed questions for review number 2. Review number 3. Review number 3 was mostly on gas laws. So we'll be going through a lot of information about gases here. Your first one, which of the following gases deviates most from ideal behavior? You're looking for a gas, if you're looking for a deviation from ideal behavior, you're looking for a gas that has high molar mass, so a really large gas, or really strong attractive forces between the two. And if you evaluate your intermolecular forces for all of these guys, these are all London dispersion forces, LDF. The SO2 molecule looks like this, though. The sulfur is in the middle, attached to an oxygen on both sides. Sulfur has 6 electrons, oxygen has 6 as well, so we get 18 electrons in this structure. I've used 4 of them up, I get 14 left. So let's see what ends up happening for our structure here. 2, 4, 6, 8, 10, 12, satisfy outside atoms first. 14, I've used them all up, so I get resonance here. I'm going to have a double bond on this side. So I get 3 things around my sulfur. I get a pair of electrons and 2 oxygens. And if I just draw it like this, just looking at the geometry, this bent shape is going to give me some polar tendencies for this molecule. And that polar tendencies are going to allow it to attract to other gas molecules, and that attraction is not part of ideal behavior. We assume for an ideal gas, there's no attraction between the molecules. So that's what makes A correct, is slightly polar. You want the most polar molecule. If you're looking for temperatures or pressures, for ideal behavior, you want really low pressures so that you don't have a lot of particles occupying that container. And you want really high temperatures so they're moving fast and not close to the condensation point. Our next one on gases. This one, I can see how you might have had trouble with this one. This one involves quite a few concepts here. Diagram 1 above shows equal molar. That means we have the same number of moles on both sides of our barrier here. I have 2 gases inside a container fitted with a removable barrier placed so that each gas occupies the same volume. So equal moles on both sides and equal volumes. This is right in the middle of our container. The barrier is carefully removed and the temperature is held constant. Diagram 2 shows the gases soon after the barrier is removed, which statement describes the changes to the initial pressure of each gas and the final pressure of each gas in the mixture, and also indicates the final total pressure. This is a Boyle's Law problem. And the Boyle's Law problem is this. We have a gas. Just picture our gray gas here. It has some initial pressure, and we know Boyle's Law is this. Pressure 1 times volume 1 equals pressure 2 times volume 2. Well, our pressure 1, it could be anything. We'll just call it P. Our volume 1, we'll just call it V as well. So this side has the volume V. Well, as soon as I remove this barrier, we get a new pressure for our gas. I'm going to call that my variable X. We're going to solve for what this pressure 2 is. So I get pressure 1 times volume 1 equals, and then volume 2, as I remove this barrier, it's going to double my volume. Well, that means I'm going to multiply by 2 times my initial volume V. Well, if I double my volume, it's going to cut my pressure in half. And if you solve for X here and divide it on the other side, we'll divide by 2V here. Our V's cancel, I get P over 2. So I get 1/2 of my pressure equals my new pressure, X. So the pressure of gas, our gray gas here, using Boyle's Law, or just qualitatively saying double the volume, half the pressure, it's going to get cut in half. So the pressure of the white one will also be cut in half. Well, the total pressure in the container is the partial pressure of each gas. And this is Dalton's law of partial pressures. P total in container is partial pressure of, I'll just call it G for the gray gas plus the partial pressure of W for the white gas. Well, the partial pressure for the gray gas is going to be 1/2 and the white gas will be 1/2. So the total pressure in the container gets cut in 1/2, a factor of 1/2 on both of these. So if we go through these we'll just jump to our correct answer for C. C, the partial pressure of each gas in the mixture is half of its initial pressure. That's true. And the final total pressure is half the sum of the initial pressures of the 2 gases. And that's correct as well. D is incorrect. D has you do the partial pressure is half the initial pressure, which is correct. And the final total pressure is the same as the sum of the initial pressures. That's incorrect. Both pressures decrease. And so the partial pressure in the container overall, when they add together, will be less as well. This question asks you to evaluate 3 different gases with given conditions and compare the average kinetic energies of the gas molecules. This is a really quick question if you understand what average kinetic energy is and how average kinetic energy is connected to your temperature. Some of you miss this because you're trying to do the more complex version of this where you compare velocities. But if they're all the same temperature, the average kinetic energies are the same. Temperature is a measure of the average kinetic energy. And so we just need to figure out which one says they're the same. That's D, they're all the same. But if we were comparing velocities here, let's do that real quickly. Your velocities, your kinetic energy is equal to 1/2 your mass times your velocity squared. If this problem said compare the velocity of each one of them, we know the temperatures are the same, so the kinetic energy on this side of the equation has to be the same. If our mass has changed, and they do, it gets more massive. The more massive molecule, as m gets bigger, our v has to get smaller. I need a smaller v for our C4H10 so that when I multiply this out, I get the same kinetic energy and end up with the same temperature. So at the same temperature, the larger the molecule, the slower it's moving. So this would be the slowest, and this would be the fastest, the methane. And lots of AP questions that involve that are talking about rates of effusion, gas particles going through a tiny little pinhole, or rates of diffusion of a gas. The smaller the molar mass at the same temperature, it will diffuse faster because the gas particles are moving faster. Another gas one comparing A, B, and C. The density of the gas is, which one has greatest density? Well, let's compare these guys right here. The best way to look at this problem is consider the ideal gas law, PV equals nRT. Well, the R is the same for all of these. Is there anything else that's the same? They're all in the identical rigid containers. That means the V is the same. They're all the same temperature, so the T is the same. So the only thing that we're comparing here are the pressures and number of moles the same. Why do I want to know the number of moles? Well, the number of moles will give me the ability to calculate the number of grams in a liter of the gas sample. So let's just compare our moles here. For A, we have a temperature, a pressure, and a volume, temperature, pressure, and volume. That's the same as C, the temperature, the pressure, and the volume, same identical container. So these have same number of moles. A and B equal moles of gas. If you just compare these two to each other, for the density of the gas, we would want the gas that has the most mass, the most molar mass. If they have equal moles, if they're both 1 mole, say, this would have 16 grams in the container, and this would have 58 grams in the same container, and our grams per liter would be greater for the one that has more grams. But let's look at our B. What happens to B? The pressure is bigger. Pressure is times 2. We double our pressure. Well, if you double your pressure and everything else is the same, the number of moles must also double. So this has twice the moles, 2 times the moles for ethane. Well, 2 times the moles, that means I'm going to have twice as many molecules at this mass in this container. Well, 30 times 2 would give me 60 grams in this container if I had 1 mole in it, or 2 moles of gas. And in the same container here, for a pressure of 2 atmospheres, I'd only get 1 mole of gas, and that'd be 58 grams for that whole volume. And so I get 58 grams for the number of liters here and 60 grams for the number of liters here to get double the pressure. And that makes B have the most density, the greatest density, which would be B. The molecular formula and molar mass of 2 straight chain carbons are listed in the table above. Based on the information in the table, which compound has a higher boiling point, and why is that compound's boiling point higher? You just want to compare the intermolecular force types here. So for this problem, we have 2 straight chain carbons. They're all nonpolar. Both of them are nonpolar. So we have London dispersion forces. Since they're both London dispersion forces, we now go to the size of the molecule to compare the boiling points. The molecule that is larger, the one that has the greatest surface area, will have the highest boiling point. And the reason for that, you have a greater surface area for the molecule to interact. If you remember us talking about Velcro, and a small patch of Velcro is easy to pull off, but if you put a Velcro suit on, it can hold you to a wall if you've ever seen those bouncing up. So part of it's surface area. The other part of it is the larger the molecule, the greater the odds of the electrons moving around. That's called polarizability of the molecule. And that means that we're going to have, even though they're both London dispersion, nonpolar, we're going to have slightly bigger partial charges on the butane just because the molecule has a bigger electron cloud. There's a greater chance of there being those electrons distributed unevenly on that electron cloud. And so B is the correct answer here. The larger molecule, it has more electrons, that's right, resulting in greater polarizability, so greater surface area and stronger dispersion forces. A greater polarizability, greater difference in charge, and more electrons equals a stronger force. And that's it for multiple choice number 3.